Okay, so good morning, good evening, everyone, wherever you are. Well, we have our third presentation lecture today about the Xcompact3D by Sylvain. Sylvain, the stage is yours.
Great. Sorry, I assume you can see my screen and you can hear me well. Sorry,
Yeah,
my voice is not 100%. I have a cold. Well, good morning, good afternoon, everyone. And so today I'm going to present you very briefly Xcompact3D, which is part of this student cluster competition. So Xcompact3D is dedicated to the study of turbulent flows. And one example on this slide is the flow generated by a wind turbine with 3 blades. And basically, the Xcompact3D framework allow you to simulate any type of turbulent flows. I'm based in the UK at Imperial College in London in the Department of Aeronautics. A little bit of background information about me. I am a reader, or it's equivalent to associate professor in computational fluid dynamics. So as I said, I'm based at Imperial College London, and here you have a nice picture of the Imperial College campus based in South Kensington, very close to Hyde Park. I led the turbulence simulation group. I am French. I also have a British passport. I did my PhD in Poitiers in France, which is a small city in the middle of France. And as I said, my research is to study numerically turbulent flows and how to manipulate them to the benefit of society. And I will give you some examples in this presentation. And to study turbulent flows, I'm using supercomputers. And I guess this is where and why you are here today. So what is turbulence? Richard Feynman, very well-known physicist, said a long time ago, turbulence is the most important and solved problem in classical physics, which was true 40, 50 years ago. It's still true these days. We are still struggling to understand turbulent flows. Here are some turbulent flow that you can see in nature. And basically, turbulence is everywhere around us. It can be the smoke of a cigarette. It can be extreme weather events, avalanches. Apparently, there is some turbulence features in painting. And on the left here, you can see the turbulence generated by a wind turbine. Unfortunately, the wind turbine was on fire, and thanks to the smoke, it was possible to visualize the wake generated by a wind farm. And actually, this setup is part of the competition. Here's another example of interest. Is when you have a moving vehicle, in the wake of the moving vehicle, you will generate some turbulence. And here you can see 2 vortices that are generated in the wake of an aircraft. The bottom line is turbulence is everywhere around us, and we need to better understand it. So, for example, if we want to predict extreme weather event, we need to better understand turbulence. And for the flow around moving vehicles, we want to manipulate turbulence so we can reduce fuel consumption, we can reduce drag, and so on and so on. And for wind farm, I will tell you a little bit more about why we want to understand better turbulence. So if you want to study turbulence, you have 2 options. The first option is you go in wind tunnels or in water tanks, and you use a reduced model of your setup, and you try to do some experiments. The other option is to do what we call a computational fluid dynamics, CFD. And here you have a few examples of CFD application. The flow around a racing car, some idealized avalanches. And here, this is the flow inside an engine. And at the bottom here, this is the flow downstream of a submarine. So as you can see, turbulence is characterized by a wide range of turbulent eddies or vortices. And this makes the turbulence extremely challenging to resolve because you need to be able to capture the smallest scales and the largest scale as well. So it's quite demanding. This is why we rely on high performance computing. So the framework Xcompact3D is designed to study turbulent flow using supercomputers. I will try not to bother you too much with equation and detail, but basically what we do is we have a Cartesian mesh, so we have a 3D box, if you wish, and we are using what we call finite difference methods, which is way of approximating derivative using Taylor series. I will be talking briefly about how do we include solid geometry inside the computational domain. That can be fixed or that can be moving. And I will spend a little bit of time about the 2D domain decomposition that might be of interest for you. The rest is not really relevant for this competition. Just to give you a little bit of history, Xcompact3D started as Incompact3D, and 3D is for 3-dimension. Incompact is for incompressible flows, and compact because of the properties of the finite difference scheme. It was created at the end of the 90s in France. It is a pure fortran code, still in 2022. It was redesigned in 2003, 2004 with modern fortran, I will say. And then in 2006 with MPI, with 1D slabs, and in 2009, 2011 with 2D pencils using the 2D decomponent FFT library. Then Xcompact3D was created in 2019. It was, the idea is we moved from solving one type of equation for incompressible flows to a wider range of flow configuration. Incompressible, compressible is, for example, water, you cannot compress it, so it's incompressible. And air, you can compress air, so it's compressible. Both air and water are fluid flow and can lead to turbulence. The code is quite small. It's about 40,000 lines of codes and about 15,000 lines of code for the 2D domain decomposition part. And we are currently working on redesigning the code for GPUs. And we are still planning to use Fortran and the amazing do concurrent feature of it. I'm not going to spend too much time on this, but this is the type of equations that we are solving. We are talking about partial differential equations. We have various quantity of interest, like the velocity, the density, and the pressure field. And those equations are not too complicated. However, they are non-linear, non-stationary, and non-local, which make them extremely challenging to find solutions. That's why we rely on simulation and approximation of those equations. The code is based on finite difference schemes. So as I said, we have a regular mesh. We have the velocity on the black node, the pressure field on the white node, and we are using this type of high order finite difference method, which allow you to find an approximation of derivatives. As I said, you can recover those relation using the Taylor series and the Taylor theorem. So to compute the derivative, you just need information close to where you want to compute the derivative, and then you can fine-tune the coefficient alpha A and B to get a certain accuracy in your simulation. In terms of high-performance computing, that might be more of interest for you. We currently have what you have on the right-hand side. So we have 1D slides. Okay, this is a 2D domain decomposition. So when we started designing the code a long time ago, we were only using one CPU. and now we can use up to 1 million CPU cores. We are able to do simulation with several billion mesh nodes. As I said, this strategy at the moment is CPU friendly only, but we are working on a GPU friendly version. And but if you are interested in more detail about this 2D domain decomposition strategy, you can go on, or you can Google 2D decomp and FFT, and you will find more information. The way it is working is that we are trying to avoid calculation and communication at the same time. So when we want to work in the X direction, we use this domain decomposition. When we work in the Y direction, we use this one, and in the Z direction, we use this one. And when we want to move from one domain decomposition to another, we are using the well-known global MPI all-to-all transpositions. It can be quite expensive, those global MPI all-to-all communication. We are doing about 70 transposition per time step for about a cost of about 30 to 80% in terms of communication. That might be quite large, but if we look at the strong scaling of the code, you can see here that we can achieve strong scaling up to 1 million CPU core. So once again, as long as you have, and this is something that you might want to investigate during the competition, I will be talking about that later, but as long as you have a certain number of mesh nodes per MPI processes, then the code should scale well. The one thing I wanted to touch about is to explain to you how, when you have a Cartesian mesh like this, and the governing equations are dealing with fluid, how do you add some solid geometry? And we are doing this with an extra term in our equation, and basically what we are doing is we are trying to freeze the velocity inside any solid geometry. So we scan the computational domain, and when we are in the solid, we freeze the velocity to 0. That's the rough idea. I'm not going to spend too much time on this. We have customized this approach so that, for example, if you want to do a cylinder, if you just freeze the cells inside the cylinders, this is what you will get. If you don't have a good mesh resolution, you will simulate the flow around the yellow shape. But if we want to do the red shape, so we have designed a reconstruction strategy so that we can locate exactly where is the solid geometry, and we reconstruct the flow accordingly. So this is a better way of simulating complex objects. And of course, this strategy is very valuable because it allows to simulate moving objects in a fluid flow. So here, this is a 2D cylinder moving from right to left in a fluid that is moving very slowly. And you can see once again the vortices and the turbulence that is generated in the wake of the moving object. But this is done on a Cartesian mesh. There is no complicated body-fitted meshes or distorted mesh. I'm just going to highlight a few examples of industrial relevance. The first, I have 3 examples. It's going to be very short. The first one is about turbulent jet. So you can see that as a plane engine, if you want. This is the latest generation of engines, and you can see this chevron or this tooth or dent arrangement that has been designed to reduce noise and to increase the mixing efficiency of the engine. What they don't tell you is that during cruise, there is a slight drag penalty, which means the fuel consumption is slightly higher than conventional engines. So there has been a lot of research by Boeing, by Airbus and NASA and so on, trying to find what's the best strategy for this chevron arrangement. What we are trying to do is we are trying to design an active control strategy where instead of having the chevron that is always there even when it's not needed, so during cruise you don't need to reduce the noise, the aircraft is far away in the sky, it's only needed during landing and taking off. So Airbus, they came up with this idea of having some fluid injection at the exit of the nozzle to reduce the noise and to increase the mixing efficiency of the engine. And during cruise time, you don't need to use those things. So the performance of the jet will be optimal during cruise. So with the Xcompact3D, we have been able to reproduce the experimental setup. And just to show you what we have found is this is a jet without any control. So you can see this is the vorticity field, which is supposed to tell you where the flow is turbulent. You can see that at the exit of the nozzle, there is no turbulence, and you have those large ring structures that are very large and very noisy, and then the flow is becoming turbulent. This is great in terms of performance. This is not great in terms of noise and mixing efficiency. If we look at the control one with microjet injection, you can see that the flow is becoming turbulent very quickly. The large rig structures have disappeared. And it means that during landing and takeoff, you can use this control strategy to reduce the noise of the engines, and you can increase the mixing efficiency of the fuel that is burned. So it has quite some benefit, and you can turn it off when you don't need it. Another example is the flow around moving vehicles, in particular planes. And one of the main issues, of course, is that when you are going through the air, you have four forces. You have the thrust, you have the gravity, you have the lift, and you have the drag. So the drag is a force that is slowing down the aircraft. It's the resistance of the air. The air is trying to fight the aircraft. So we need to find ways to reduce the drag. So we are looking at a flat surface here. And what we are going to do, we are going to try to do some vertical blowing. So we are going to add some air, okay, and try to see if you can reduce the drag penalty and therefore increase the efficiency of the aircraft. So this is a simplified setup where you have the flow coming from here to here, and then you have a control area where you are going to do some clever blowing. And here, this is a map of the friction coefficient. If you are below the black line, it means that you are achieving drag reduction. Okay, the black line is the reference case, and you can see that when you are doing the blowing, you can reduce substantially the drag, and you can even produce some energy saving. Okay, not going to spend too much time on this. We use the Bayesian optimization to try to find the optimal parameter for the blowing that will produce some energy saving. So by reducing the drag, you are going to allow your aircraft to travel at the same speed, but using less fuel, using less energy. And the final example is wind farms. And this is actually part of the competition. If you look at modern offshore wind farms, they do not produce as much electricity as expected. And the reason is about turbulence. So if you look at those fancy pictures, this is the wind farm, the Hornrev wind farm in Denmark, in North Europe. You can see that usually wind farm, the wind turbines are clustered in very close to each other. And here we can see the wake generated by this C07 turbine. You can see it's directly impacting all the turbine downstream of it. And unfortunately, wind turbines are designed for a clean airflow, a clean incoming airflow. So this one and this one are going to produce a lot of power. This one and all the ones that are in the turbulent flow are not going to produce as much power as expected. So it's important to understand how wind farms are operating. Just to give you an idea, I think it's difficult to realize, but the modern wind farms are based on turbines that are more or less the size of the Eiffel Tower. There's very large, more than 200 meters diameter. So we are talking about very large scale turbine. So in order to do that, and this is exactly what you will have to do for the student competition, we have a nice setup with two turbines. So one turbine is here, another turbine is downstream of it in the turbulent wake. And here, this is a time evolution of the power output. And you can see that the power output for this experiment is between 4 and 5 kilowatts. Okay. Now, if you decide to shift a little bit the second turbine, so this is what we are going to do very soon. So now the two turbines are not exactly in line, they are staggered with each other, and you can see that the power output from those two turbines is much higher. It's because the turbulence that is affecting the second turbine is less important. You can see now the power output is oscillating between 8 and 14 kilowatts. So this is the flow setup that you are going to investigate. These are more visualization of wind farm that we can do with Xcompact3D, and of course that are directly relevant to industry. One final slide about the control. So we have different ways of operating those turbines. We have the greedy mode where you ask each turbine to generate as much power as possible without taking care of the other ones. And this is the time evolution of the power in megawatts. This is a 4x4 generic wind farm. You can see that the power is about, let's say, 17 megawatt. Now, if you ask the turbine to talk to each other and try to be cooperative, so try to change the yaw angle, so try to change the direction of the wake, then you get the orange curve, and you can see the power output has been shifted up quite dramatically from 17 megawatts to let's say 21, 22 megawatt. So there is an advantage in trying to understand turbulent flow and how they are affecting wind farm and wind turbine. I'm going to go through the task for the competition. So I'm going to stop sharing my slide. I'm going to now share my internet browser. So you have all the information, of course, on how to get started with Xcompact3D on the competition website. There are different sections. If you're interested to know more about the code, there are you find the GitHub. You can find the website and a paper describing Xcompact3D. This is an overview of the solver with two papers presenting the numerical methods. There is a little bit of background information about the wind turbine simulation, basically, and of course some information about how to download the code and compile it. As I said, it just needs a Fortran compiler and an MPI library, and you're good to go. So compilation is very straightforward. It will take you 1 second. I've just provided you some examples with on Niagara with the Intel and Intel MPI modules, and for Bridges 2 with OpenMP and the GCC compiler. Of course, part of the competition will be to investigate different Fortran compiler and different OpenMP library. If you want a sanity check, there is a well-known test case called the Taylor-Green test case, where you can very quickly run the code in 3 minutes and look that it has been installed and it's running properly. What is of interest is try to play around with this setup of wind turbine, where you have two wind turbine. The second one, they are in line with each other. Okay, this is what we are trying to reproduce with our simulation. There's a very limited number of tunable parameters. This is P row and P code correspond to the size of the 2D pencils. Okay, and you can play with the number of time steps, how many time steps you want to run your simulation for. You will not need to change more parameters. What we are interested in this competition, we are interested, of course, in profiling on Niagara and on Bridges 2, try to compare the performance of those two machines. One is based on AMD cores, the other one on Intel cores. So there will be some differences. We are interested in performance analysis by depending on the fortran compiler, depending on their options, depending on the MPI library, depending on the number of MPI processes per node, and the size of the 2D pencils. So the bulk of the competition will be to find the optimal combination in terms of fortran compiler, options, MPI libraries. How do you tune the MPI network? How do you tune the number of MPI processes per node, and so on and so on? This is what we are expecting mainly for you. There is also a section about producing some nice visualization of the flow. So you have all the information here. This is done with the software called ParaView, which is very easy to use. You have all the instruction here, but you should be able to produce some nice visualization. And even if you have time and the resources, you should be able to produce some nice movies. So you can see the turbulence moving as in my presentation. And there's a small bonus task about looking at a strong scalability study on Niagara and Bridges 2 using 1 to 8 nodes, and try to see what strong killing you get on those machines, and maybe try to identify some potential bottleneck. Right. I think that's pretty much it for me. This is we have a Twitter account. There is a GitHub for the Xcompact3D, and I know you cannot click on those links, but yeah, if you Google Xcompact3D or Incompact3D, you will find all those information. And as a reminder, if you're interested in the research that we are doing, just Google Turbulence Simulation Group, and you will find us very easily. So I believe now it's time for a Q&A session. So if you have any questions, if you have any comments, I'm happy to answer everything you throw at me.
Well, thank you, Sylvain. It was very, very nice to hear. Anyone has any questions, feel free to put it in the chat or just speak.
Excellent. Everything is clear.
Everything
is easy. Yeah. So there is a question on the chat about code optimization. So you are not expected for this particular part of the for this particular task. You are not expecting to play with the code. What you are expecting to do, for example, you are expecting to play with the compiling options. So, for example, on the if you are using the Intel compiler on Intel hardware, you will find that some compiling options are making a massive difference in terms of, for example, vectorization and so on and so on. So the competition is not about trying to modify the code, but it's instead trying to find, you have on each machine, you have different compilers, different MPI libraries, trying to find the sweet spot to get the best performance, the best time to solution. If you have to run, let's say 1000 simulation, what's the best compiler options, and MPI library and environmental setup to run those 1000 simulation in the shortest possible amount of time. So that's the motivation of the task, and you will find some big differences depending on the compiler and the compiling options and the MPI library. So it's going to be quite interesting to investigate this. What's the main motivation for using Fortran over, say, C? Is it just simplicity of porting from Xcompact3D? Does Fortran provide? Well, I could easily reverse the question. What's the main motivation of using C? We are using Fortran because the compilers, Fortran compilers, are very mature, and they are producing code or executable that are extremely fast on CPUs. That's the main motivation. The second motivation is that there's often question about using C++. We don't require any advanced features from C or C++. So we are very happy with Fortran. Just to give you I'm a strong fan of Fortran. So in the UK here, we have a super computing facility called Archer 2, and which is a machine with 750,000 cores. And we have reports every month of who is using Archer 2, and 80% of the codes are based on Fortran. I don't know if this is just a fact, but yeah, the main motivation is that the compilers are very mature, are very fast, very efficient. I'm not saying that for C it's not, but that's the main motivation. The new motivation, and this is brand new, is that there's the do concurrent feature in modern Fortran, and companies like NVIDIA are embracing this feature. Their compiler can recognize the Fortran do concurrent when you're doing a 3D loop, and it can generate some CUDA code automatically in the background with OpenACC, pragmas, and stuff. So it seems that we already have evidence that we are going to be able to use our Fortran code on GPU as well. So that's another strong argument for using a Fortran. Yeah, that's the main answer. Okay, Fortran, no capital. if we want to be pedantic, yes.
Okay, let me add something here. One is we're using the Xcompact3D also for the coding challenge. We will have another session in 2 days. And over there, as Sylvain said, we are going to change the all-to-all calls to I-all-to-all. But once you investigate and profile the application, it will help you also for the coding challenge to understand how it works and what are the main calls and message sizes. And the coding challenge is basically taking this application into a deeper place, trying to understand the code and use it in a cluster with the CPUs, but also what we call DPUs, data processing units, that have some kind of CPU, ARM CPUs on the network adapter. We're going to talk about this in 2 days, but just gives you a heads up on this. So
yes. So as I said, just to add a little bit, at the moment the code is based on MPI all-to-all communication, and there is no overlap of calculation and communication. So part of the coding challenge will be to look into this using this DTU hardware technology to see what can be done to improve the time to solution and performance of Xcompact3D.
Okay. Any additional questions? Anyone? Another photons forever. Another reminder is I'm always on the Slack channel. So if any question, you can always contact us on the Slack. You can always find us on the email. Feel free if you're stuck, if you have any issues, let me know. I assume that by now, by the way, all of you have already access to the clusters, to all the clusters. If you don't have any, if you stuck for some reason, if you don't have access, let me know and we'll figure this out. And another reminder, on Monday, we're going to have a kind of a formal opening ceremony. So you're welcome to join. And we'll have several speakers and we'll introduce the teams, introduce the application, the charges, some talks. And that's it. So get going. And if no more questions, I would like to thank Sylvain. It was very helpful, very nice to hear all the talks, this talk about that. Very nice about the airplanes. Actually, I like it as well. So it's nice to see that science is helping the industry in different ways, and it's also important. So when you're doing something, you help the society, you help the world. So by that, I would like to thank everyone for joining, and I will put the recordings on the website. And again, if you have any questions, just ping us on Slack, and we will try to help as much as possible.
Absolutely.
Okay.
Thank you very much, everyone, and good luck for the competition.
Good luck, everyone, and thank you.
Thank you. Bye-bye.
Bye-bye.
Thanks.